So, as some of you know, have been working for many years, almost 20 years now, on titanium dioxide and on various aspects of titanium dioxide related to photocatalysis, both materials aspects and reaction mechanism. So I will not present here an overview of photocatalysis, but just give a brief introduction and also present some more recent work, which I think I'm more excited about, and so I just last thing. Actually, the last thing is not even published, still under writing. So, let's start a little bit. Oh, first of all, I'd like to thank all the people who have been, actually many people may not have been listed here. There have been various postdoc and students in Princeton. One of them is Uli, who is here, and some collaborators in Italy, like Andrea Vittadini and Cristiana, and then Di Valentin. And then I have a long-time collaboration with Ulrike Diebold in Vienna, and now also her postdoc Martin Setvin. The people who have been doing most of the work that I will present today, at least the new work, are Sencer, is a Turkish student. He has been a student first, and now he's a postdoc, and now he is leaving to go to Mark Hybersen, so that Alfredo knows, and Xunhua is a new postdoc coming from the group of Matthias Scheffler in Berlin. So, as an introduction, I don't know if it is very clear. It's a little bit, a lot of light, but as many of people may know that titanium dioxide is among the most popular metal oxides. It's not only abundant and expensive, it is non-toxic, biocompatible, photostable, so the stability is an important issue, so that many of the more performant materials do not have. And it is very widely used for many different applications, going from very simple ones like, let's say, pigment in paints, and even you find it into the toothpaste and sunscreens, to more, let's call advanced applications like photocatalysis, and which was initiated by Honda Fukushima in 1972. Dye-sensitized solar cells that everybody knows very well here in PFL. They were introduced by the group of Michael Gretzel, and there are also new advanced applications in memristors. Those in red will talk more. And also, to complete the story a little bit, is that titanium dioxide, like many oxides, comes in many forms. There are many crystalline forms. So there is the stable crystalline form is known as rutile, and it is stable. But the form which is called anatase is the one which is found most frequently in nanomaterials, and is also the phase that it is considered photocatalytically more active, at least in many cases, not universally, but for many applications. So anatase is what I will be talking mostly about, anatase TiO2, and here it's a brief summary of the principle of how photocatalysis works. So it is, here you have to think about a semiconductor particle or nanoparticle, and photocatalysis essentially consists of 3 steps. First, there is a photon which is absorbed, creates an electron-hole pair. Electron and hole very often tend to recombine, but sometimes they quite often also they separate, and then they tend to diffuse to the surface. And then at the surface, if there is an adsorbed molecule, they can transfer and initiate a process of reduction and oxidation. And so this is essentially the last step, which is a electron or hole initiated oxidation or reduction process. So these are the 3 basic steps. Dye-sensitized solar cells, as I said, should be known very well by most people at PFL. Essentially, here again, there is an important role of the transport of electron. So this is a nanostructured film of anatase nanoparticles. The gray are anatase with some adsorbed molecules, which are these dyes. And once you inject the electron in the nanoparticle, they have to travel to the electrode. So there is an important role of charge transport in all these processes and devices. And this is something that we would like to talk about. So in this application, the electrons and holes are often, in the case of DSSC, are photo-injected, in photocatalysis photo-excited, but there is, it is quite well accepted that the behavior of photo-excited electrons is quite similar to that of excess electrons. So what I mean excess electrons? Excess electrons are essentially the electrons which come from impurities of defects. So in these EPR traces from the group of Elio Giamello in Torino, which shows APR for different types of anatase. This is photo-excited anatase, and other are anatase having electrons coming from various types of impurities. And you can see that the signal is very similar. So it is an indication that the behavior is quite similar, either of electrons coming from dopants and impurities or from photoexcited from photoexcitation. In particular, TiO2 is known as a reducible oxide, so it tends to lose oxygen pretty easily and have oxygen vacancies or titanium interstitial, which provide excess electrons. And so the material tends to be an N-type semiconductor. And indeed, most of the interest is in the presence of these excess electrons, which make it an N-type semiconductors. Sometimes you can also dope intentionally, like using a niobium. Niobium is used to make anatase a TCO, what's called a transparent conducting oxide. So many of the interesting properties of this material come from the fact that there are these excess electrons in the materials. So when you talk about these excess electrons, or electrons which go into the conduction band because the valence band is already full, so one of the important questions you might like to ask is whether these excess electrons behave like delocalized conduction band states. So they are kind of plane wave state which have a dispersion like a free carrier parabola, or they tend to become localized and form so-called polarons. So the simple picture is here. So this is the free electron parabola. To cause localization, of course, you have to make a distortion of the lattice. So this would cause a strain energy, and so you have to pay an energy to distort. But this energy can be compensated eventually by some electronic energy gain. And if this electronic energy gain is larger than the strain energy, then you get into this localized polaronic state, and the energy of these states tend to go somewhere in the gap. And there is a simple rule which says that the more is this localized electron, and the deeper is the state into the band gap. So you can so distinguish between so-called large polaron, which are like shallow impurities, which are it can lead to good conductivity, and small polarons, which are really in a deep trap state, and so these are not good for the conductivity, and particularly also in dye-sensitized solar cells. So what is known is that in rutile, and electrons tend to form like well-localized polaronic states. These are calculations we did several years ago with Cristiana Di Valentina and Gianfranco Pacchioni. And so here these are these gap states coming from an oxygen vacancy at the surface, and these are well below the conduction band. They are localized, and these are the charge density associated with these two excess electrons. You see the typical contour plot of the electrons, because these states come from states in the conduction band which are coming from titanium. So these are like 3D states of titanium, so these have this typical shape. So it is quite well established and known that in rutile these excess electrons are localized, form small polarons. It has been for quite a while a little bit more doubts and debate about the character of the excess electron state in anatase. And actually there is evidence from experiment of both shallow and deep states in this material. So these are photoemission experiment by a group in England. I think in this paper there is also Michael Gretzel inside. So here they show photoemission for different incident photon energies. Here on a rutile 110, which has been very much studied for many, many years. And you see this feature that I highlight with a red circle. This is this defect state, which is this polaron, which is about 2 eV above the valence band. So these are the field state that you see in photoemission. In anatase 101, you have a similar, probably even more pronounced state of similar character, a defect state, so an indication of a small polaron, a localized state. On the other hand, on another surface of anatase, it is 001, there is no such state. And more recently, there was a paper also from a group at the PFL, which showed that actually on this surface you might find a shallow state, about with a very shallow 40 millivolt binding energy. So there is an indication that the behavior that you find in anatase can be dependent also on the surface facets that you are looking at. You can have either deep states or shallow states. This is another recent experiment which combines STM and STS. And here in this surface they create in a surface oxygen vacancy, a defect, which gives rise to a deep state. On the other hand, there is another feature on the surface, which are these halo that they are attributed to subsurface niobium impurity. In this case, the spectroscopy gives a very shallow state, about 0.1 eV below the conduction band. So there is this dual phase. They are both deep and shallow state, which have caused quite a bit of trying to understand where they come from. And so we will return in more detail in a little while. And now it's a little bit more digression on some general properties of anatase. So I want to talk a little bit about the surface properties. Because you have seen when you start doing experiment, very often you probe the surface, so you have to know a little bit more about the surface. So this is an anatase sample. Even if it is metastable, you find it in nature and has this typical bipyramid shape. These are instead colloidal sample, and you still find this shape, which can be also calculated. And it is made mostly by two surfaces. One, it is this majority, which is, I mean, the surface which is really by far most frequent, it's most stable, and turns out also little reactive. And then there is this 001, which is a small amount, but instead it is interesting, has attracted also a lot of interest in the last 10 years or so, because it's thought to be specially reactive, so to have some special properties. So what I'm showing here is an STM of anatase taken by Ulrike Diebold 8 years ago. So that it is that was a kind of new thing at the time, because it's not people didn't have for a long time samples of anatase large enough to make surface science experiments. So what she had a natural sample that on which she was overgrowing with MDE to make it more smoother, the surface. And so what you see in this surface, you see various features. Of course, there is this island which has this typical trapezoidal shape, which is actually it is consistent. You would always find the islands of this shape and with this orientation. Then there are other features, I hope you can see that, which are indicated by these arrows. So this is a feature which took a lot of time to identify what it is. It's just a water molecule. There are other features which are seen like brighter halos, and these are subsurface impurities. And there is another feature actually which is very interesting, and the feature is actually the absence of a feature, because there is no surface oxygen vacancies apparently on this surface. And why this is so surprising? First of all, I said TiO2 is reducible oxide. There are always vacancies. Okay, so it is surprising. Also, it is surprising because in another surface which has been very much studied, is this rutile 110, there are lots of oxygen vacancies, which are all these little pieces, which are, there is a circle here, which is these straight lines of titanium atoms, and then these little segments, connecting lines. So these are oxygen vacancies. And they are about between 5 and 10% of oxygen vacancies on this surface, which are not found on anatase, and that was kind of surprising at the beginning. And so it took some time to understand that here the vacancies actually tend to be below the surface. The surface likes to be as perfect as possible, and this is also supported by our calculation, which shows that the vacancy formation energy is lower if you go below the surface at the very surface. And this is indeed a further proof of that, is that if the surface, which is what is called here the pristine surface, as cleaved, which is so perfect, is subject to electron bombardment, which is known to create vacancies, oxygen vacancies, so you would find this kind of little feature, like this little bright feature. This is a blow up, and this is what we see, and this is a calculation of the STM image for an oxygen surface oxygen vacancies, which gives indeed a confirmation that okay, if there were oxygen vacancies, surface oxygen vacancies, they would look like this, but actually, unless you form it on purpose, they are not there. And there have been further experiments. I will not spend the time more on that. So it is a surface which is kind of peculiar. It is robust, stable, has a low energy, is robust, and also a little reactive. This is, I think, the first paper I did on this material a long time ago, and it shows, for instance, to probe the reactivity, what people do is to study the absorption of typical molecule. Water is certainly an important molecule, and it turns out that water indeed does not dissociate, remains molecular, forms this nice structure. That also this has been confirmed by experiment. So this is a calculated image for a water molecule compared to a experimental STM image, and you see there is a very nice qualitative agreement, but even quantitative, which we were able to calculate the image, to calculate the corrugation along typical line scan, and have a very good comparison with experiment. So this is so this shows some of this aspect of this surface, and this aspect of being so little reactive, when the reason is it's not only for a single water molecule. We did the calculation for over layers of several monolayers of water, and these are molecular dynamics simulation. This is a very old, again, a very old slide, but which has been repeated in many times. There are some of the things that need to be checked again and verified many times for different purposes. But so there is this fact that there is no dissociation, which is shown also at high coverage, and actually agrees very well also with these are temperature programmed desorbed experiment, which show no indication. There are various peaks corresponding to various adsorbed species, and no indication of dissociation, which would give a feature around 450 degrees from the general know-how that one has on these surfaces. So, and actually, we were even able to have a quite good quantitative explanation of these TPD. So I'm not going here, which gives, from this simulation we can extract. So, but just as it seems, everything seems nice and goes perfect agreement, but it's always not everything, it's always in perfect agreement. Actually, there are also things which are not understood. For instance, now understanding the interface between water and an oxide, in particular TiO2, which is a kind of prototypical example of an oxide, is something that experimentalists are very much looking at, and there are lots of various experiments popping out all the time. And for instance, also on this surface, there are indications that actually at the real water interface with water, dissociation takes place. And so this is something that we should revisit somehow to understand why when we go to this real water interface, there is actually dissociation that we would not observe in some other types of experiment and in our simulation. So now this was just a kind of very general introduction. Now what I would like to discuss, tell you a little story about some work that we have done on trying to understand of the dynamics of these excess electrons on this anatase 101 surface, and also on different surfaces, and also the interface with water. So the approach that we use here to study these dynamics is to do direct first principle molecular dynamics simulation of this excess carrier that is following an approach which had done a few years ago but at the interface with water, with vacuum. And so under this approach, we are assuming that the motion is adiabatic, so essentially the electrons remain in their ground state. And also, this is an approach which is interesting, but is very difficult to obtain the estimates of mobilities. But it's interesting to get mostly qualitative ideas of how is the motion occurring. So just to give you an example, these are some other computational details. So we use an approach called DFT plus U that the computational people here know very well. There is an issue, which is that these U, there is some uncertainties, so we have to check what is the effect of U, and we use two different U's. But this is a kind of technical detail that maybe is not interesting to everybody. But so let me start now my story about this motion of the electron. So what I'm showing here is a slab of this material, so exposing this 101 surface. Here there is an excess electron. You see here it is localized on a titanium. It forms this typical D state. And it is immersed in a liquid environment. So these are two side views from different angles. And so we start with the electron at this localized in this site. And then what we want to see is what happens. Okay, so you start seeing some motion. The electron jumps on the other side, and we keep simulating, and then essentially nothing really happens. So these sudden jumps actually is just a technical feature of what they're called periodic boundary conditions. So what it is here and it is here is the same thing. So it is actually the same electron, which is always in the same place. So the result of this simulation are summarized in this graph. What I'm showing in this graph is essentially these dots give the position of the electrons. These are the different layers, as you see here, 1, 2, 3, 4, 5, 6. So there are 3 double layers here. And say this is where the electron here, it was on a layer here, then it jumps on a little above, and then it remains for the rest of the simulation. This gives the probability distribution, and this is the number of titanium sites on which the electron is localized. And so this says this electron is localized only on one titanium atoms, and so this means it is a small polaron at the interface between, so the electron is trapped. The electron is trapped at the interface between the titanium dioxide and water. And this is what we observe, and then we decided to do other types of experiment. Now, there in that case, the electron was coming from an adsorbed hydrogen atom, which is a donor. It gives an excess electron. Now, instead of having a donor at the surface, we have a donor inside the surface, which is here, inside the slab, which is here. It's an interstitial hydrogen. And we want to compare what happens if I have a system in vacuum and a system in water. The same identical system where there is this hydrogen and generating an excess electron, and exactly the same thing. So here it's so we see, you can see already that here it is in vacuum. The video is, I don't think it is a great quality, but anyway. And here is what happens in water. And in water, it goes directly to the surface, and there it remains. Let's go to the, oh, sorry. Doesn't want to go on. Ah, here it is. So this is, we call it hydrogen doping. So there is an hydrogen here in the middle of the slab, which generates this excess electron. And so these are these graphs that say where the electrons here is. So these are the surfaces. And here is the probability distribution, the number of titanium. So you can see that there is a significant difference from the behavior of these electrons when the slab is in vacuum and when the slab is in water, when it is solvated. And where it is solvated, the electron likes to stay exactly at the surface and to be localized on a titanium atom. Here it's much more mobile and jumps around, as you have seen all the time. It finds the surface, but still quite jumpy. So a similar behavior actually happens even if we generate this excess electron with another type of impurity, which is an niobium donor, which is here in the middle of the slab. If we compare the behavior in vacuum, you see the electron is very mobile, which is positioned all around, and it is spread on many titanium atoms. And in this case, instead, after a short while, it finds the surface and remains at the surface. So there is a clear indication from this calculation that we have done on several other systems. These are just a few, that the water environment makes electron trapping. There is this trapping effect at the surface much more favorable in vacuum. So incidentally, trapping is something that, for instance, you would very much like to avoid in something like a dye-sensitized solar cells, because of course if the electron is trapped, it is not contributing to the current. So trapping is not something that you like. So this would tell that water would favor the trapping at the interface. And so this would not be very nice. And so one would like to ask why there is this trapping induced by water and there is not in vacuum. One could say, is it a solvation? Turns out that it is something interesting. We were talking about water not dissociating when it is on this 101 surface. Actually, what happens is this electron induces water dissociation. And here are some snapshots taken, given a sequence of this water dissociation event caused by the trapping. So there is electron here. It involves two water molecules. It is a quite complex, and this is a proton which is shuttled by this water to the bridging oxygen site. So here, because here is a proton. At this point, this proton here stabilizes a lot of this electron which is there. So, and this makes all the story, all the system much more stable. And so the electron likes to be stabilized by this proton, and so induces the dissociation of water. So, and so this is a kind of unanticipated effect, which is evident also in you calculate this radial distribution function of water. So you see that the black trace is when there is no excess electron. There is usual, it's very similar to what you find bulk water. And here, when you have this excess electron, it gives this peak, which is due to this presence of this hydroxyl at the surface. Okay. Don't know why. Do not disturb. I don't know what it is happening here. It's got stuck. Maybe it is. Oh, I can see. I get news alert. I'm getting news alert from CNN, but.
Do not disturb.
What should I do? I think I should click here. I think I should. Oh, yes, it is here. All right. Okay. No, I think I will skip this story. Sorry, this is more. I want to discuss a little bit this issue, which actually I think it is pretty interesting. So, so of course we are using some simplified model to discuss all these things. There are many approximations, many size effects. So what we were worrying here about is what is the effect of the finite size of our slab in the behavior that we are simulating. So, then we decide to explore the effect of this, what if you say a confinement effect. So we have been working with this slab, which has a certain amount of layers, and say what happens if we use a much thicker slab. So we are always consider niobium as a source of the electron, which is here in the middle in this case. Here it is green in the thicker slab. So here is 4 double layers, 7 double layers. When we are in vacuum, essentially there is no substantial effect. The electrons is always very mobile, and it's a kind of shallow polaron. It's a large polaron. When we go in water, the behavior between the small slab and the thicker slab is slightly different. So here, in the case of the small slab, you see there is a perfect localization at the surface, and no more story. The electron is trapped at the interface. In the case of a thicker slab, there is a little bit more competition, and so it is indeed a competition between the fact that the electron resents the attraction of this donor, of this impurity here, so tends to like to be somehow close to the impurity, but at the same time is also attracted by the surface, and so the two are competing for taking the electron. So this kind of behavior actually can be modelized quite easily with a simple model, like considering a particle in a box with 2 wells. So we model the interface well like a thin and deep well, which is here, the black line is the potential, and the potential from the niobium impurity by a shallow and wide well. And what happens is that if you look at the ground state of this double potential well, this double well potential, it happens if the 2 wells, the shallow and the shallow well and the deep well are close enough, then the ground state happens here. It is the green line. It is here. If they are, this is the separation of the two wells. The ground state is here. The two cooperate in making the ground state favorable here. If the two wells are at a sufficient distance, a distance larger than the radius of this well, now at this point, what becomes the ground state is actually here. It has kind of more favorable to be at this state. And this is kind of this behavior. So when the separation is very big, so this gives pretty well. There is this competition between being attracted by the narrow and deep well or by the shallow and wide well. So this is some other facts that we have learned about this behavior of excess electron. And there is something about the facet dependence. Here is another surface which I have not discussed so far. It's actually a pretty stable surface which favors trapping even more than the 101, because we observe a trapping even in the case of a very thick slab at the surface. But even more interesting is the case of this 001 surface that I've mentioned at the beginning. And this minority surface, which is shown here, what we observe for this surface is that actually it is shown here. This is the polaron. You see, the polaron is actually completely delocalized, and it doesn't go to the surface. It tends to avoid the surface. These are this kind of plot. We summarize the position of the electron. So these are the surface S, and this here and this here. And during the whole simulation, the electron stays away from the surface and tends to be delocalized and forming a kind of two-dimensional behavior in these layers. And I know the two-dimensional behavior is quite typical and seen also by Professor Chergui in this material, in the excitons. So they have this two-dimensional behavior, and it occasionally jumps from one of these 001 layer to the other, the electron, but it remains like that. And this actually has a kind of simple explanation. So this surface is a kind of natural band bending at the surface. If one looks at the projected of the layer is all densities of states for this surface. The density of states for the top layer, really the outer surface, is a higher energy. So there is a kind of what we call the bands bend up. So both at the valence band and at the conduction band, they go up. And so this prevents the electron to go to the surface because it has higher energies. So, and this actually also turns out to provide, to give an explanation for these observed, from this observed lack of a defect on the 001 surface. The 001 surface, the electron cannot go at the surface, remain subsurface, remain in the bulk, and in the bulk they are essentially large polarons. So the summary I would like to give is that these dual, I don't know, this is not probably the best summary, is that indeed we observed this double behavior of large and small polarons in anatase. Large polarons are essentially the bulk polarons are large and mobile. And these are useful because they give a good conductivity. This is why anatase is a good N-type semiconductor. Electron at the interface, they can get trapped if there is water or if there is a defect like an oxygen vacancy. And then this gives the small polarons that are sometimes seen. So there are small polarons, but the small polarons are at surfaces and interfaces and defects. And in the bulk, you have large polarons, mobile polarons. So this is the message that we think, at least it's, people were starting to say this type of message, but I think this simulation provide a good illustration that this is indeed the case.